talking about some statistical models of crop response and how we can use them to understand crop response to climate and under climate change. Now, a couple preliminaries, I guess. For the last few years, I've been working on understanding the impacts, the economic impacts of climate change and climate volatility in East Africa. So I'm neither a climate modeler nor an agronomist. So my perspective on crop response and using climate data is very much that of a collaborator of climate scientists and agronomists and a consumer of their research. Hopefully a better consumer over time. And so that's the perspective that I'm going to try to share with you over the course of this afternoon so that you too can become hopefully better consumers and better collaborators of climate scientists and agronomists. Just a brief outline of what I'm going to be talking about. So I'll focus on panel data and time series models of crop response estimation. There's another broad family of statistical methods to look at crop response, and that's the Ricardian approach pioneered by Mendelssohn and others, and that's been used to great effect. I won't be talking about the Ricardian approach, but we can talk about it over the coffee break if we ever have one, and outside as well. So I'll focus on some of the big global studies that have been done recently and try to tease out the long-run forecasting capabilities of these models, as well as their ability to look at volatility, climate volatilities, and the response under extreme climate. And as I said before, more so than the actual results, I'd like to focus on some of the insights that I've gained while trying to apply these methodologies to economic analysis. And that's something that that may make more sense when we go to the next presentation, when we try to link them to economic models. So just a few general words about the statistical modeling of crop response. So over the last day or so, we've looked at some very powerful, sophisticated, process-based crop simulation models. And so you might be wondering, why would you want to be worried about statistical models at all? Well, you know, they actually have some attributes that that are appealing to some. First is that they abstract away from the biophysical processes, and I think that's something that I got a sense was shared by some colleagues in this room, that not all of us may be familiar with dormancy or evapotranspiration or ability to absorb solar radiation. And so by focusing directly in a reduced form mechanism on the statistical relationship of climate variables under some functional form to yields or production or some other metric of crop production, we can look at the relationships between the climate, under climate change, directly on agricultural output. Another characteristic that makes statistical modeling appealing to many is that it provides a statistical measure of accuracy. If you're worried about how accurate your model is, you've got an R-square or some measure of model fit that you can refer to, and that can hopefully provide some support of the truth of your analysis. And finally, it doesn't need calibration. So the process-based approaches, while powerful, require a lot of data and need to be calibrated, validated, etc., which you don't necessarily have to do with an econometric approach. So a lot of the literature today uses international time series and panel data, whether it's production, yield, etc. And this has really taken off in the last few years, led in a large part by David Lobell of Stanford and his colleagues. And they've produced a series of seminal papers, I guess the oldest one being the 2008 paper that appeared in Science, and more recently a 2011 paper that just came out last month that expanded the use of these statistical models. The general take-home from these is that under climate change, the impacts on yields, on production, are going to be negative. And this is in the least developed countries in the tropics. And you'll recall that this goes back to what David Zilberman was talking about yesterday, when he talked about climate change moving production from the equator up to the poles. And that's exactly what this is a robust result that this body of literature supports. Another big take-home from this body of literature is that temperature is often has a larger impact on yield on production than precipitation. Just to illustrate, this is an old paper from Lobell and Fields from 2007, where you can see that the marginal effect of a change in temperature on yields, on interannual yields of 3 major crops, and you can see that it's quite uniformly negative. Since we're in Africa, and I'm sure most of us are interested in climate change in Africa, I think it's worth focusing on at least one of these major studies. And I picked the Schlenker Lobell study that came out in Environmental Research Letters last year. It's an open access journal, so everybody can download it even if you're unsubscribed. So what Schlenker and Lobell did in that paper was they took production data from FAOStat for the last 4 decades, the last century, and they estimated yield response for several major crops to climate variables, with the climate data coming from a few different sources: the National Centers for Environmental Prediction and the Climate Research Unit in East Anglia. That's what they used for their estimation. For generating predictions under climate change, they relied on climate output from 16 different general circulation models, and they picked the output from the middle of the current century. So just a few words about their model, which you can see here. This is a general representation of their estimation equation. Y is basically the log of yields, and then they explain that using a country dummy, the C, a time trend variable, so time in quadratic form to capture the effect of technological improvements, and then they have a function of weather. So they actually look at 4 different specifications of their estimation equation for each crop and country. And I'll just run through them very quickly. So the first specification was one where they looked at average temperature and precipitation over the growing season for the crop in the country. The second specification looked at the same growing season average temperature precipitation, but in quadratic form. The third specification looked at precipitation over growing season in quadratic form, plus a linear piecewise function of temperature temperature degree days. So the number of days that temperature was between 10 and 30 degrees Celsius, and then the number of days that temperature was above 30 degrees Celsius, to capture the impacts of these extreme climate thresholds. And their fourth specification was, once again, precipitation in quadratic form and a linear piecewise function where they looked at the number of days within, I think, 4 different categories of days with different temperature ranges. They estimated these models, and they found that the results are robust to their model specification. Now, one thing that they did here in order to capture to compensate for the uncertainty of looking across all these different climate models was they generated the predictions for the future using the climate model inputs, and then they calculated a change in the yields from the average in the historical period. And then they pooled the results to generate a distribution of changes in yields between the 2 time periods. All right, so it sort of captures the whole the potential, the envelope of possible responses over the different models. Oops. So now that they have distributions of crop response pooled across the different climate models, okay, looks a bit more colorful here. They have pooled responses by crop and by country. We get nice figures like this. So, so this is just for 4 crops, some of the 4 most interesting crops, and they start from the left-hand panel, from the left-hand side, where they look at the lower end of the impacts distribution, so the 5th percentile, where the responses are the worst for each crop, each country. And it's hard to see here, but basically every country in Africa is going to be experiencing negative yield changes over the time period, and it's robust across all climate models. Some countries affected more so than others. For example, South Africa will be hit particularly badly for maize. The same result is, the uniformity of the result is true for maize as well. Every country in Africa is going to have a negative change in yields. When we finally move to the 95th percentile, the more optimistic end of the range, we see that some countries will start to experience mild improvements in yields for sorghum, millet, and groundnuts, but for the most part, it's still pretty bleak. And once we generalize, there's a 95% probability, with the exception of cassava, there's a 95% probability that the yield response is going to be at least a 7%, sorry, at least a 7% decline in yields, optimistically, and pessimistically, it could be as high as 27%. So that particular study and other studies looked at these long-run impacts. But we know that climate change isn't just a change in average temperatures over time periods or average responses. It's a distribution of outcomes, right? And that's where this idea of extreme outcomes and volatility comes into play. So there's evidence that climate extremes are as important for agricultural output as average values, and that climate volatility is not just going to increase in the future, but is already increasing in many cases. So I'll just jump to an illustration from a paper that I wrote with several colleagues at the Bank, Stanford University, Purdue, and elsewhere, where we try to capture this idea of climate volatility and agricultural variability. So my colleagues went and collected data, yield data for the 17 regions in Tanzania, and they estimated the crop response, the yield response of maize, rice, and sorghum to temperature, to growing season temperature, precipitation over the 1992 to 2005 period. All right. So once they estimated the model, we were interested in understanding how this would, what the impacts of climate change would be using this approach. So what we then did was we took climate output from 22 different general circulation models picked out of the Climate Model Intercomparison Project. It's open access as well. So we took data from these 22 different climate models, and then we bias corrected them to historical data from the Climate Research Unit. So one thing you might notice if you work with these models is that even for a historical period, the climate data won't necessarily be what was actually observed. So what we do is we use a statistical approach so that the volatility in the historical period at least matches up to the mean and the variance over the historical period. And then we generate predicted yields over the historical period as well as over a future period. In our case, the historical period was 1971 to 2001, and the future period was 2001 to 2030. So usually when I show this table, people's heads explode, but I'll try to be, but it has some insights. So here we have the 22 different models that we looked at, and their names aren't that relevant for the point that I'll try to make. Here we have the average change in the period temperature and precipitation, and the change in the average yields from between the historical and the future periods. Now, if we come down here, we see we have a measure of sign consistency. So we know how well the models track this change in average values between the two periods. And we see that, well, you might not be able to see, but it's 1 or very close to 1. So they're very good at looking at, they agree a lot in how much on average the climate and on average the crop response is going to be. The second set of columns looks at the percent change in the standard deviation of those variables between the present and between the past climate and under the future climate. And what we see when we come down to the sign consistency is that when we're looking at temperature volatility, changes in temperature volatility, the models generally agree. It's got a sign consistency of 0.52. But when we think about precipitation and yield, they're close to 0. So they don't agree much in terms of the effect on how volatile yield variability is going to be. And this is a very difficult question because whenever we take these results to policymakers, they don't care about about academic discussions about which climate model is closer to the truth. They want to know, what is it? Don't give me 22 different models. Just tell me what it is. But that's very difficult to do. So what we've done in this case, since we're interested in the range of potential responses, we picked 3 models that had the largest and the smallest changes in climate variability, and then we pooled the responses. So once again, going back to what Schlenker and Lobell did, we looked at the interannual changes in yields in the historical and future periods, pooled across the results based on those 3 GCMs, and then we represented them in these simple box and whisker plots. Okay, so the lower box refers to the distribution in the 20th century, and the upper box represents the distribution in the 21st century. And just looking at it, it doesn't seem like much has happened, right? But 2 things have actually occurred. First, we see the median response has actually shifted leftwards. So the median response of yields to climate variability has been a small decrease. And then when we look at the ends of the distribution, we see that the extreme outcomes have become slightly more extreme. Okay, they're low probability events, but when they do occur, it does make a difference whether your yields are falling by 20% or 25%. So I think I'm out of time, so I'll just wrap up here. The big take-homes from this are that the panel data approach can be a powerful tool, and some of the big take-homes are that temperature can be more important than precipitation. Generally, yields are going to decline in the future, especially in Africa for most crops. Climate change isn't just a shift in average temperatures, average precipitations, but is also a change in the distribution of these outcomes over a time period. And that extremes are definitely going to be something that aren't just going to be a problem in the future, but that are a problem now. And that's and we found that policymakers are very sensitive to that. It's easier to tell them, you can apply a policy that can address extreme outcomes now, and that's also good for extreme outcomes in the future, which it comes back to this idea of no regrets policymaking. Finally, we can use bounded envelopes and bias correction approaches to sort of compensate for the uncertainty of working across different general circulation models.